So we've seen that classical novae are the explosion of a thin layer of hydrogen around the surface of a white dwarf. The mass slowly builds up as more stuff gets dumped onto the surface till eventually the pressure crosses that magic threshold and the whole thing goes kabloom and explodes.
And one of the interesting things about these objects is they're not all the same. Sometimes you'll get great big explosions that happen very rarely, and other times it'll be smaller explosions quite frequently. And we think this has a lot to do with how big the white dwarf is. Because you can imagine if you've got a really heavy white dwarf, it's going to have a lot of gravity, which means that the hydrogen's going to want to blow up when there's not very much there. And so you'll get quite frequent small explosions. But imagine a bigger white dwarf, or sorry, a lighter white dwarf. Well, that's one which has less gravity, and so you can build up a lot more on the surface before it goes kaboom.
And you might also have different sorts of things being dumped on the surface. For example, if you have more helium landing on the surface, that might fuse at a different, need presumably a higher pressure and temperature to actually fuse that, but it would still happen eventually.
Yeah, because there are these binaries. It turns out when you make these binaries with a white dwarf and another star, sometimes they do a very intimate dance with each other, exchange bodily fluids, and in the process end up converting a lot of it to helium. And so you might dump helium onto the white dwarf instead of hydrogen. And helium you have to get really hot and really dense before it's going to ignite.
And presumably it's not just going to be a single explosion, but if the explosion blows stuff off, there might be a thin layer left behind which is not degenerate anymore. In that case, it could just burn for a while like a normal star.
Yes, and we also have the possibility that you can actually burn material rather when it gets on the surface, that you actually burn it on the way in. So you have hydrogen coming from a star, burning as it reaches the surface of the star, and essentially being accreted as helium. And that allows you to essentially make the star grow heavier and heavier over time.
But if the white dwarf is growing heavier and heavier, I mean, we've known that the degeneracy pressure is holding it up, these electrons moving at relativistic speeds because of the uncertainty principle. But I wonder if there's a limit to that. And I'm, of course, not the first person to wonder about this. The famous Indian astrophysicist Chandrasekhar was worrying about this in the 1930s. Let's see what his calculation came out as.
Okay, let's do the calculation. Can you really pile more and more matter onto the surface of a white dwarf without something nasty happening to it? Is there a limit to how hard this degeneracy pressure, this quantum mechanical electron pressure, can push back? Well, from our calculation earlier, we derived the radius of the white dwarf by balancing the downward force of gravity against the upward force of the degeneracy pressure. And this gives us some clue right away. You can see it depends on the mass of the white dwarf to the 1 over 1/3 power, so 1 over the cube root of the white dwarf mass. So this means that as the white dwarf becomes more massive, the radius becomes smaller. Not very fast. You can increase this 8 times and this will only halve in size. So this would seem to imply that white dwarfs can survive almost any amount of mass. As the mass gets bigger, the white dwarf gets smaller, but as the white dwarf gets smaller, its quantum mechanical pressure gets bigger and bigger, and so you just end up with very, very small, very, very dense white dwarfs without limit to the mass. So, end of story? Well, no, of course. And to explain why it's not the end of the story, we're going to have to make a little detour into what makes a star stable.